Hi class, this lab is constant pressure calorimetry. Thermochemistry tends to be a little harder for some students, so if it helps, I would suggest that maybe you read the chapter first or read the section on calorimetry to help you understand, as well as enthalpy. Excuse me. Thermochemistry is the study of heat and energy. So we're going to be conducting chemical reactions and the heat that either is given off or absorbed during these reactions. And the units that we're using is 1 cal equals 4.184 joules. That's the conversion. In this lab, we're going to be using calories. In others, we might be using joules outside of this. The system. So you need to understand what the system is. We have an open, closed, and isolated system. Next week, we'll be using the isolated system, but this week we are using an open, a closed system. So the difference between these is an open system is just like a coffee cup being opened and it's got hot coffee in it. The heat is leaving into the surroundings. It's the same as a fireplace with wood burning. Eventually, that heat from that is going to warm the room. A closed system has a lid on it. We are trying to maintain everything in that closed system as much as possible. So this is sauce, sauce in the stove with the lid on. We are trying to control the heat. Yes, the heat can leave, but the mass is going to be staying in that container. And the heat will leave, but it'll leave on a little slower pace because it's not completely open environment. And isolated is a well-insulated thermos. You don't know if you have cold solution in there or a very hot solution, because if it's really well insulated, when you touch that thermos, you can't tell. So endothermic and exothermic reactions, when excuse me, when the heat is transferred from the surroundings to the system, the reactions absorb heat from the surroundings. I'll cover Q in a minute. Exothermic is when heat is transferred from the system to the surroundings, and reactions transfer heat to the surroundings, such as a fireplace. Endothermic heat is added to the system. So when you have an ice cube in your hand and it's cold, the heat is actually being absorbed from your hand and being taken into the ice cube. The ice cube is then using that energy to change from a solid to a liquid. It's melting and it needs that energy to do the phase change. So energy is being absorbed. Where exothermic, it's being released. Think of a fireplace. If it heats long, you have fire in there long enough, it will heat the room. And Q is the heat. It is the measurement of heat, a specific measurement. We're going to do calculations, so we're going to calculate Q. And that is the flow of energy, the heat. The plus and negative sign are simply directionality. They're telling you which way the energy is being flowed. So if it's absorbing energy, it's a plus sign. And if it's a negative sign, that means that heat is being released to the surroundings, like a fireplace. And here's just another visual to help you understand where the arrows directions are going into the system or out of the system and into the surroundings. So here's Q. We're going to start using Q for this lab. So let me explain it. Q has one unit. It's either joules or cals. This is helpful to remember this. When you are given problems, you can dissect them. And when you know units to things, it makes it easier to read the problem. Q is the symbol for the heat flow, and it could have a negative or positive sign. If it's negative, it's exothermic. If it's positive, it's endothermic. M is mass, so whatever we're looking at, that's a mass in grams. C is the specific heat. I'll be covering that in a little bit. And delta T is the change in temperature. It's always the final temperature minus the initial temperature. We don't care about what happened in between. It's a state function, so we only care about start and end, and we always subtract final minus initial. So here's some terms I put together with heat capacity, specific heat, and heat of reaction, which is Q, what we just covered right here. This is just to help you understand a little bit more about this. Enthalpy. Enthalpy is another term. Simply, it is more complicated, but I'm going to explain it as simple as I can for this lab. It's a measure of heat at constant pressure. Key thing has to be constant pressure because we are not using an isolated system. It is going to be at constant pressure. So we are measuring enthalpy, that's heat of reactions, either reactions that have used up energy or released in reactions. Okay? And so Here, when a chemical reaction occurs, a substance can become warm or colder. As a result, the heat will flow to things around it or or from things around it until the temperature is the same again. So that's what they call thermal equilibrium, and that's what we're going to do in one of these labs today. If the pressure stays the same, this amount of heat tells how much enthalpy has changed. So basically what that means is that constant heat, we will use enthalpy as the heat of measurement, measures the heat, excuse me. So I'm going to do this a little different, where I'm going to cover part C first. It's the easiest one to understand. And once we do this one, then I hope the other two will make more sense. So specific heat, everything we touch, everything we come into contact with has a specific heat value. It's a fingerprint for that substance. And what that means is how much heat can it take before it starts raising the temperature. So if you've ever jumped into a cold pool on a hot day, even though the sun's hitting both, the temperature in the water is much colder than the concrete that just burned your feet. That has to do with specific heat. Water can hold a ridiculous amount of heat before it'll even raise a temperature 1 degree, where anything else that has a lower value, it doesn't take much. So here's a picture of gold and water, same masses. They were heated for the same amount of time, and what you see is gold goes to 90 degrees Celsius very quickly. Water barely even raises a few degrees. That has to do with specific heat value. Water has a huge specific heat value compared to metals. That's why we use pans for cooking. They transfer heat. They get hot very quickly. We transfer heat. They transfer to the food. Nobody wants to sit for 6 hours cooking an egg. So you want to use things in certain contexts that will help you get to, eat that egg or whatever it is that you want to make on the stove. Excuse me. So that's why if you've ever boiled water, it seems like it takes forever to boil the noodles for the mac and cheese, because it does take a long time. It needs to take in more and more energy to raise that temperature. So when you go to the ocean and you're walking in the sand and the sand's burning your feet, but yet when you get to the water, it's very cold, that has to do with specific heat values. If you take a look down here, I have the posted specific heat values. Silicon dioxide is sand. It's very, very low. It's not even 1. And then water is above 4. So this is in joules. Oh, look at, I messed up. Sorry. This isn't, I think this is joules. This is not Cals. I messed that one up. This is, I wrote joules. Anyways, this, you can see just this value here is extremely large compared to any of the other values, which I'll show you a chart. That means that water can hold a lot of energy, and it will not raise the temperature very much. And at night, it will release that heat, and it will keep the temperatures of those coastal communities pretty warm. To us, it may seem cold, but that water is actually keeping those cities warmer than what they would be. If you drive inward, like to the desert, things start getting colder and colder and colder. Water holds temperatures better around coastal communities compared to if you're going inward. Start driving more inward, like deserts get really cold compared to maybe what's by the ocean. I work in Culver City. The weather over there is nice compared to San Gabriel Valley, because the water helps that in the summertime especially. But it is colder at night, but it's not as cold as it could be if you keep driving in. So water, the ocean water, will help maintain energy. It'll keep the energy without raising the temperature, but it'll also release that heat at night, and that also helps the temperatures around those cities. Substances that have smaller values don't do that. They get heat up very quickly, and they put out that heat very, very fast. So here's a chart of of substances. So as you can see, metals have a very, very small numerical value. There. Oh, I messed up. So it's 0. It's 0.835. So I messed up on that one. But it doesn't matter. You can see here that even 0.835 is still far lower than 4.184. I tend to use joules because of my other labs. We use joules, but this lab is calories. So let me focus on calories. So water here is 1.00, but everything else here you can see is low, except for strawberries. Strawberries is very high. Yes, they check everything. Cheddar cheese is on here and so forth. These are 3 units compared to Q, which was 1 unit. and specific heat values are all positive. Part C, your answer should be a positive number, not a negative number. Okay? Excuse me. So now you saw Q, and we're going to rearrange it. My throat never starts acting up till I record. We're going to rearrange it for specific heat. So you don't actually need to know another equation. It's the same equation. You just got to know that it changes. And when it changes, it gives 3 units compared to 1 unit. So specific heat of a substance is exactly what I explained. We are going to do, part C is we're going to be given a substance and we're going to figure out what the specific heat value of it is. And normally in my lab, you would be given a sheet to reference and determine which metal you had based on your numerical value. So Q is the heat of reaction, M is the mass of the substance, C is the delta T, the change in temperature from final minus initial, and we have 3 units here. So here's an example. Calculate the specific heat of water if 83.68 joules is required to raise the temperature of 4 grams of water by 5 degrees. We are rearranging Q, and then we plugging in numbers. So I don't like that they did it here. I never do this. I rearrange the equation first before I plug in numbers. But if it helps you do it the way it makes sense to you. So we rearrange this around, and joules, remember I told you it's 1 unit? So if you remember these things, it makes it easier for you to understand what the question's asking. Plug that in, mass, temperature difference. It didn't give you a temperature difference, but it did give you the temperature. You can use that. And then it gives us 4.184 joules, which is the specific heat, grams over Celsius, which is the specific heat value for water. This should never be negative value. It should always be positive. So calorimetry is the measure of heat transferred by measuring the temperature changes of the substances involved. We use coffee cups and we insulate them to try to prevent heat from leaving our experiment. In this case, the system is our chemical reaction and the water is the surroundings. And ideally, we don't want heat to be removed from this, but that's not completely possible because we still open the lid to put something in it. But we pretend that we do this so quickly nothing leaves. So let me explain this lab. For part C, we are going to heat up a metal. And once we heat up that metal to as high as we can, we're going to transfer it to room temperature water. This should say room temperature, not cold. And the amount of heat lost by the metal is going to be transferred to the water. And then eventually the water is going to warm up and the metal is going to cool down. And both will be in thermal equilibrium, meaning that they will have the same temperature. So part C, we're going to take the temperature of room temperature water in a coffee cup before the metal is transferred. Then we're going to heat the metal. And this test tube only has metal in it. It is dry metal. It is surrounded by water on the outside only. We take the temperature of the water as it's boiling as the temperature of the metal. Then right before we transfer it, we take the temp and then we transfer this metal very quickly in here. And then we close it and we start taking temperature of what's happening. And then we take the temperature until the temperatures has not changed for several minutes. That means it's stabilized. It's in thermal equilibrium. Then we're going to take that information and we're going to calculate the specific heat of the metal. So here is my information I got from LabFlow. There's brackets, so that should help you. This is information that is given to you. So I've explained it here, what we need, but I'm going to explain it on the next page. I was given zinc, so this is the information. So what I did with that information is I broke it up. I'm going to do this a little differently because the way that books tend to show you how to do it is very confusing. And one mistake means that everything's wrong. So I tend to break this up into two parts to keep it so that you understand what you're doing. And if there's an error, you usually can catch where the error is at. So here's my mass of metal, my temperature of the metal. This is the boiling. This is my initial metal temperature as well. And my final temperature is 24.6. Since they both are going to be in thermal equilibrium, both have the same final temperature. My temperature of water at room temperature was 22 degrees Celsius, and I had 100 grams. You notice that water didn't jump at all, pretty much, but the temperature of the metal did. That is the difference between metal and water. The first thing we're going to do is calculate the heat gain. So we're going to calculate Q for the water. That is the energy that was transferred from the hot metal to the water. And then that energy, we're going to plug in and get the specific heat value. So first thing is we got to convert the moles of water to grams. Using density, the moles cancel out. We have the grams of water. And then we're going to plug this in. So we have 100 grams of water, our specific heat value, which is right here, and then our temperature difference. 24.6 minus 22, and that gives us 260 cals. So we now know the amount of energy that was transferred from the hot metal to the water. Now we're going to plug it in. Now I'm using equation 14.1. It has a negative sign here, and we're going to plug this in. If you do this right, it will cancel out the negative sign. So I have my negative 260 cals. This is an exothermic reaction. I have my mass of the metal, and I have my temperature difference from here. So do you see it's a little weird? Because 99.4 was my initial, 24.6 is my final. That gives us a negative 74.8. Those negatives cancel out, and I have my substance, my specific heat of substance. Okay? Now, part B, heat neutralization. When you hear the word neutralization, you should always know that has to do with an acid and a base. Remember, double replacement reactions have neutralization as part of them. This is a neutralization reaction. The enthalpy, we are going to be determining the heat being given off or being absorbed during this reaction. And I can tell you right now, this is an exothermic reaction because an acid and base, when they come together, they give off heat. If we were to do this with very small amounts in a test tube, you would feel the heat on the test tube. This is an exothermic reaction. Now the next thing, it's a neutralization. So we are going to assume this is complete neutralization. There is no acid, no base left over, only water. So we're going to use water's values for everything on this. So if you're wondering where this information is coming from, it's water. We're strictly looking at the water. So here is the information to start with. A student adds 50 mils of HCl to 50 mils of sodium hydroxide inside a coffee cup. Calorimeter. Places the lid. The solution was at 20 degrees Celsius before. So the acid was at 20 degrees 20 degrees room temperature before the combination of being added with the base. Let me start over. I'm getting confused with my own talking. So before the reaction, it was 20 degrees, and then after they were combined, is 40 degrees Celsius. Specific heat of water, we're going to use that again, and we're also going to use the density. And we are going to assume the density is that the acid and base is water. So that means that we're only looking at the product of water for our information. So again, I pulled out all the information, and I put it out where it's easy for me to see it and understand what's going on. So first thing is I convert the volume to mass. So I add the volume of acid and base together. That gives 100 mils, but I'm using the density of water. It's going to give me 100 grams. Now I'm going to plug in Q. So Q has 100 grams of water, my specific heat of water, and the temperature difference. It's giving me 2,000 calories. And this is my information that I used here. But we're not done. We need enthalpy. So now we're going to take 3. We are going to lab flow is going to specify it once the acid, even though these are the same molarity, sometimes that's not always the case. So we're going to take the molarity of acid and we're going to determine the moles of the acid. So I get the moles of acid, which is 0.15. Now we're going to get to 4, which is equation 14.7. We're going to plug in the 2,000 calories. We're going to plug in the moles, and that's going to give me a value, and I'm going to use my sig figs, and it's going to give me the value that I calculated in following rules. And that's it. It's not a difficult lab. It's a pretty straightforward lab if you follow the rules. And there's a lot of equations on PDF. So on the PDF, so look them over as well. So number 5 with the brackets, I put my 2,000 calories. My number 6, I showed you how to get that. Number 7 is here. I entered a positive value for 7, and that's it. And the last question will be the average of the 2 trials. I never entered units. And most of these, you're not going to be able to enter units, except for the averages, it might ask you. But I never enter, as you can see, there's kind of a trend. I never enter units on lab flow. Now, part B. Part B has 2 solutions of salt. So you're going to be doing one with ammonium nitrate, and then another with magnesium sulfate. I'm only going to show you how to do ammonium nitrate, but it follows the same rules. The problem is one of these, and I forgot a little plus sign here. This should be a plus. One of these is endothermic, and one of them is exothermic. Do not let that sway you. Follow what is given to you and just go with it. Okay, so this is a dissolution of a salt. So it's soluble in water, so it's ionized. It's going to break apart in the solution, and that's going to give off some energy. Either it's going to take an energy for this to happen, or it's going to give off energy for this to happen. So in this case, we have 3.1 grams of solid ammonium nitrate, and we're going to add it to enough water to make a solution of 60 mils. The resulting temperature of the water of the mixture drops from 20 degrees 0.1 to 16.7. So this temperature went down. That's always a sign of either endothermic or exothermic. And now we're going to calculate the energy per mole for this. So this is very similar to number 4. So here's my information for this one. I have my mass, volume, and so forth. Convert the mixture. So this is the mixture of 60 grams. So I have my water. Sorry, this is my water. This is my water of, I'm repeating this because I actually had a problem with LabFlow on this one last semester. I noticed they had errors on this one. I contacted them asking for confirmation of how to do certain problems because their PDF didn't match how to do the problem on LabFlow. And I explained my problem, and it's just like getting bad customer service anywhere. I told them what I did. I told them the answer's not coming out right. And all they did was respond back with exactly how to do the problem, which matches their PDF. But again, LabFlow wasn't matching how to do it. I had to get creative to figure out how they were accepting the right answer. It looks like this semester they fixed it, so maybe there was enough complaints that they actually fixed the problem. So I just got a flashback of that, of going back and forth with people there. So anyways, we have 60 mils. We're going to get 60 grams of water. The temp difference, final minus initial, is negative 3.4. So you should put a negative if there is one on LabFlow. The temp of the system decreases. It absorbs heat. That gives you an idea. When the temperature drops, that's an endothermic reaction. Now, number 3, we're going to determine the enthalpy. So we're going to use the Q, because this is at constant pressure. Q of the solution equals the enthalpy. So we're going to plug in this information. We have a negative sign here. So 63.1. 63.1 is my mass of water plus my mass of the salt. This was a problem on LabFlow. They were only counting this when they should be counting the whole experiment. And I kept trying to tell them that, but they were telling me they weren't reading my emails, pretty much, is what it sounded like. So this here, this number matches this and this. So let me make that clear. So if you're looking at where that number come from, just add them together. And then we have our specific heat of water, and then we have our temperature. That the two negatives cancel out, so this ends up giving me 210. Now this is a little weird here because you see that I didn't round here. LabFlow is going to ask you specifically for this number, so that's why I rounded it to my sig figs. However, when I continued on with the rest, I did not use this one. I carried it on with this one, knowing where my sig figs are, because I never round any of my answers until the very end. But this one specifically asked for one answer, so I gave it to them in the correct form, but then I went on with the unrounded one and continued on to the very end. So here we go with, now we need the moles of ammonium nitrate. I put a line under where the sig fig is, and then I carry that over, and then I get my amount. I follow my sig fig rules. This is equation 14.8, and this is set up in the same thing, Q with the moles, and plug it in. So B and A are very similar, and then C is very different. But by doing C, I think it makes A and B hopefully a little easier to understand on how to do these. There's a lot of information, but if you follow what needs to be done and make sure your calculations are right, you'll be fine. Now keep in mind, you have 2 salts here. So one of these values, by the time you get to number 5, this end, one of these should be a negative number and one should be a positive number. Just like the temperature, one should be a negative and one should be a positive. So if you leave the negative sign off or it needs it, it's going to count it wrong. And you're going to be like, well, what did I do? It's because you missed that. So follow the equations and use the negatives when they need to be. Don't question why it's there. They're there on purpose. And in certain reactions, they'll cancel out, and others, they're not meant to. So here is, I broke this down a little bit. If the temp is negative, do not forget to use it. So this is my little warning to let you know. Mass of salt, this is the solution. So this is where I added everything together. If you get a negative number, put the sign there or it's going to mark you wrong. I've also given you the molar masses of these in the section. And pay attention to temp difference. The temp difference is going to tell you if it's endothermic or exothermic. I did not use units on lab flow. I never do. And it still seems to mark me right. Okay, and now here's a question that's similar to what you're going to be asked. I've taken some shortcuts on this. I hope you guys can still figure out what I'm doing on here. It's easier for me to explain this way. I was trying to do it in another way and it just wasn't coming out the way I could explain it well. Determine the final temperature when 100 grams of water at 21.7 mixes with 75 grams of water. So now we're simply looking at water. One's hot, one's cold, and we want to know what the final temperature is between these. So I'm trying to look at this as a distance instead of a temperature. So we're going to start at 1 with 21.7 and it's going to go up to a certain amount. And then we're going to start with 71 on one side and it's going to go down a certain amount. So this X is, in some of these questions, they really get weird, or not weird, but complicated, where X is a value and then you have to plus or subtract it from something. This case, we're not using more than one variable because they're both going to end at the same temperature and we're not doing anything more. When we solve for X, we're solving for the final temperature. Okay, so the colder water will warm up and the warm water will cool down and eventually they will end up with the same temperature. And that's going to be the Q lost equals Q gained. But, and this is how they want you to set up part C, but you'll see why. It's kind of a nightmare. That's why I break things up. So one's going to lose, one's going to gain, and eventually we're going to end up with the same temperature. So delta T on one side is 71.0 minus X, and the other one is X minus 21.7. Because the final temperature is going to be warmer than what they started with. And the other one's going to be the initial, the difference is going to be when the final is going to be on this one, cooler. But the way I set it up, I'm also removing the negative sign from the formula. So that's why these look a little different. If this doesn't make you comfortable, you can always Google how to do these. Believe me, you can find any of this information online and you can see how other people do it. I tend to try to remove things that screw up people when they do this stuff. So split apart and set up Q for both. So there's going to be Q water 1 and Q water 2. This is how they want you to do the specific heat metal. So you see where the line is. This looks very confusing. This is why I did part C in 2 steps and not like this. Because when you're learning how to do something, this is really easy setup to mess up and make a lot of mistakes. So I took shortcuts on this one to try to avoid that. Trust me, I got the right answer. So X is the final. So what I did here is I just canceled out these. I canceled out what was similar on the same side. How do you do that? Well, you divide one when you divide the other, and that removes it. And then I removed all units. I removed all units from everything because it makes it easier to do the math. So now this is what it looks like here. And I just did the math. It's plain and simple. As long as I know what I'm ending with, I can plug that in. So I plug everything in. I moved every variables to one side and everything without variables to the other. And I solved for my answer. And this is very similar to 1411, the PDF, where I just removed the negative sign as well. By changing one of these temperature differences, I removed the negative sign by doing that. That's algebra though, so you guys should have some idea of what I'm talking about when I'm saying I'm doing that. Anyways, it got me to my final answer. You're going to have a question like this somewhere in the report or somewhere in the quiz. So this is very similar to that, and this should help you understand how to do that. Okay, read the PDF well. Again, thermochemistry takes a while. That's where we're going to have 2 weeks on it. You have 2 weeks to study this. All the equations I use are in the PDF. Pay attention to negative signs. Use them. I've highlighted where they tend to be needed. If you had them, take your time. And it appears when I was looking at this that there might be 2 attempts. That's what it was showing on my side. But I'm not sure about that because I don't know if you guys are supposed to have that. So if somebody entered 2 attempts for you guys, yay, that's great. So if you messed up on one, you still have a second attempt to do it. And that's it. Thank you.